Today we have Dr. Jesus Torres. He teaches acoustics at the violin making school in Mexico, and he gave a presentation several years ago on his research doing simulations and measurements on the Titian Strad. So this is a follow-up to that, and I think he's going to summarize all of his findings over the past couple of years. Jesus?
Thank you. Thank you, Fan, for the opportunity, for the invitation. That's correct. I think that my presentation 3 years ago was one of the first, maybe the first. I don't remember exactly. But, well, this is the title of this talk, Studying Violins Through Laser Experiments, Computer Models, and Data Measured on Violins Through Several Years. Thank you, everyone, to be here. My name is Jesus Alejandro. Please, if you have a question or a request or comment, anything, please use both mails to ensure that your message is received. This is the abstract that you receive in the invitation. So let's start. As I was saying, 3 years ago, we showed the results of a project about making copies of the TCM violin. The dissemination of the work in this forum was incredible. Several people contacted us to ask the codes, the papers, questions, including the editor of the Strad magazine. He invited us to write a small paper about the project, about making violins using the scientific data available in the project of the Strad 3D project. Well, let's start with the state in this moment. I will be presenting some results on recent papers published by the lab. So if you want to go deep in any topic, please feel free in making a question or sending an email or any way that you want to contact me. I will try to not go too deep in every concept and let you to choose what do you want to talk, okay? In this first paper on Caldersmith measurements of free plates and assembled violins, well, we have a lot of measurements of Graham. Sadly, Graham Caldersmith passed away 5 years ago. I have a lot of his experimental data. In these boxes, we had found a lot of data like this. He measured frequencies, weights, signature modes of violins in several stages of the constructions. In this paper, we are showing an analysis of a particular data. We are sorting the second free mode of top plates in ascending order, and the rest of the graphs keep this order. We're trying to looking for this link between free frequencies and signature modes. Already, we know that this link is hard to find. But I think that having more data to show this connection or to show that this connection is hard to find, I think that is useful. As you can see, it will be hard to say that you can control directly any of the signature modes. The same is true for the fifth-free mode. Using the fifth-free mode is not a guarantee that we can link with any other of the signature modes when the same violins are made. These graphs correspond to 38 violins and is available at Technical Note in Acoustics Australia. If you want the paper, please contact me. Once we have seen that free plates and signature modes are hard to connect, we focus our attention in the ribs. This is another paper about this. In this paper, we measured a violin, a real violin, this violin, and extracted the measurement data to visualize it in a free software. What do we want doing this? Firstly, a tool for the students. Now we can see the vibrations in any point of view, real time, over the frequencies, and you can remove the parts, as you can see. You can remove the parts that you don't want to see. If you keep the ribs, you can see how is the motion of the ribs over the frequency. And the motion is very important. So we think that, at least in my lab, we need to put more attention in the ribs. We think that we need to develop more tools for experimental developments about the violin. This is a technique where you can see the vibrations of a system in a very simple experimental setup. You only need to send laser light over the structure that you want to study, and you can see the vibrations naked eye. You can find this paper with this technique explained for to be implemented in any classroom at any level. Of course, we use this technique to see the vibrations of a violin. This is a paper available in Applied Acoustics, where we can see how the signature modes of the violin are revealed for this technique. As you can see in the figure 6 here, this is the CBR mode. It will be hard to find a relationship between the CBR mode in this technique and the classical nodal lines in this mode. This is so because this technique reveals very different information of the vibrations. They are not revealing nodal lines. The technique is revealing the parts with more vibration. And this is very interesting, I think. And this technique is very powerful to be playing with this phenomenon. And it's very simple to implement. In fact, we use this technique as a complementary technique to see interferograms in an optics lab. Why? Because when we were measuring interferograms, we need very small amount of vibration in the order that we cannot hear if the instrument is sounding. We cannot hear the sound when the test was running. But the laser strict patterns technique, this technique, reveals us naked eye if the violin was vibrating. This is part of a paper, again in Acoustics Australia, named Vibrations of a Violin While the F-holes Were Sequentially Cut. So we have a violin without F-holes, and we measure the instrument. Firstly, we had found that even without F-holes, signature modes appear clearly. But the most interesting part of this project, in my opinion, was exploring about the bridge hill. The bridge hill, the hump around 2 kilohertz, the bridge mobility of the both instruments. A finite element model, the finite element model presented 3 years ago, revealed that bridge hill appears even without the presence of the F-holes. It was very interesting for us because over the years, scientists have been trying to link what part of the violin is more linked with the bridge hill emergency. Okay. Firstly, as you know, we think about the bridge rocking motion, the island, the bridge feet. But at least in my case, I really thought that bridge hill depends clearly on F-holes. But simulations denied this. We need to check this with experiments. And as you can see in figure 11, the bridge hill appears even without F-holes. Of course, when we are changing step by step the F-holes, well, we have some changes in the response. As you can see in this text, solid line without F-holes, short dash, F-holes, straight parts. We include these funny symbols to illustrate how the F-holes were cut. Dotted line, lower pad cut, like the shoes of the F-holes, and long dash, finished F-holes. Around 1 kilohertz, we have more changes in the bridge hill response, or in the bridge mobility response, while the bridge hill changes, but without disappear in any case. Okay, finally, we have the simulations and the experiments. I mean, we create a violin for this task. And finally, this is a very quick talk. Finally, I want to show you this paper. It's available in Revista Mexicana de Física number 70. Is just a few days ago it was published. It's free to everyone. You can go to the website of the magazine, the journal, and download right now if you want. The name is Differences in Violin Sounds Caused by Changes on Arching Profiles. This is the abstract, this is all the reference. Because one of the main conclusions of the previous papers was that we need to do more experiments in violins. Models, well, in all the models, we need to remove parts to improve the understanding. But we have found that there is no like measuring violence in finished violence. But we have some explorations that we cannot do on violence like this, changing the arching profile. This is impossible to do in experiments, at least for us, because you cannot change the arching profile in a violin. So in this paper, we take the finite element model of the JASA paper of 2020, and we updated this in several ways. But we are not simulating now the Stradivari violin, the Titian. We are simulating now this violin. Even so, the goal was not to obtaining a mirror of the real behavior of our violin. We only are looking for a general behavior like a violin, to test the main question of the paper. And we consider that disagreement between experiments and simulation is enough. Of course, if you want peaks matching perfectly, well, this is task for another kind of work. What we want to show is what is happening if you are lowering the arching profile or if you have higher arching profile. And this is the responses. As we can see, for the case with the high arching profile, we have a slightly increase in the frequencies, as expected. Empirically, makers know that higher arching profiles can be linked with a brighter sound. Or if this is not true, this is not important right now because we can hear it. This is the main addition to our model. Now we can hear the sound from the model. We promised you this in our last paper or in our last talk in the VSA Oberlin seminar Friday, first Friday. We reached this step with a lot of help of Team Woodhouse. He guided me some years ago the best way to do that. So thank you, Jim. Thank you, Fan, for this contact. Thank you to everyone. In fact, we are very excited to show you this. So now we can hear it, okay? So firstly, we hear the tapping the bridge. Okay, I don't know what the music say. The sound from the models, and next we hear two notes. I hope that you can see my cursor. Yes, yes, yes. Okay. I am saying that because I will turn off my microphone. Please, if you can turn up your sound, it's time to do that. But you need to see what is the sound that you will hear, because I am not speaking right now, okay?
Yes,
Well,
so yes, we can hear it. It's very faint, but I can certainly hear that the second one is slightly higher in pitch.
yes, well, my opinion is equally of your opinion. I can hear a slight higher pitch for the high arching top tone. But the meaning of this in the notes is the most important part, I think. So now we hear the G note. And finally, D note. Okay. We are very excited for this tool. What is it means? We have the same materials, we have the same ribs, we have the same thickness, we have the sound pot exactly in the same position, we have the same bridge. It's the same model. We are only changing the arching profile. And we can hear, I hope, changes in the final sound. It means that the only reason that we have different sounds was decided for the maker. This is very important for us. Well, I know that you already know from several years ago, but now we have a tool to explore this. Talking with Sam Simontovic a few weeks ago, we are playing with this software, and he asked me, "Hey, we need to change this and this and this to hear it." Okay, this need a lot of work, but now we have this tool, and this is the end of my presentation. This is all the reference of the papers he's shown, except the guitar sounds. It was not presented, but it's available too, where we are talking about the guitar and his history. So, thank you.
All right. Thank you very much. Thank you very much. So Joseph.
Yes, thank you, Jesus. As always, it's a pleasure to hear what you've been up to. The last one, I found it odd listening to the two when you played the impulse response, the tap. It seemed to me like a clear difference, almost like two keys on a piano, with the second one higher. The high arching sounded higher in pitch. When you played the G and D string, I heard something much more subtle and almost the reverse. It would have been probably 50-50 whether I would have guessed it right. I'm curious, was it just my deteriorating hearing, or did other people feel this?
Joseph, my reaction was that I heard a clear difference between the high and low arched for the two notes, but I didn't attempt to match it up with the tap tones. I'm not sure that absent further training, I would be able to.
But that's just so interesting, because for me, it was almost ridiculously obvious. Of course, I could be mistaken, but I thought in a blind test, I think I would get that right 10 times out of 10. Whereas the listening, the reconstruction of the played note, I felt no such feeling. I'm just curious what other people heard there. And Jesus, what do you find obvious and not obvious?
Well, I must say one thing. You and me, and maybe several people here, we're very familiar with tapping the bridge in violins. I think that all the violins in my hands are submitted to this test. So we have experience trying to link this sound with the behavior of the instrument. But expecting that if the tap tone is higher, and then all the notes must be higher, is not a help. It's not in this way, because as you know, you have the same response but with peaks, with higher frequencies. You are more well. The arching profile is moving the response to higher frequencies, but the notes are the same for every violin. So you can obtain the spectrum that this higher pitch in the tap tones can be meaning changing all the content. So it means that not all the notes must be higher in the partials. Okay, it was clear, my idea?
Yes, and I completely agree with it. I wouldn't have expected a pitch change, particularly in any of them, rather than a color change. But I seem to hear a pitch change with the impulse response.
Yes.
But I would have expected the reconstructed notes to be perhaps brighter in timbre for the higher arching, and I didn't really hear that. I'm curious. Jim, what was your reaction? You're used to listening to this sort of thing and thinking about it.
I would be interested to hear the same thing with convolutions done with the kind of G-string recordings that we've been using in our bridge project, just to get away from that single note. I'm sure you hear something different just with every different single note. It just depends where the overtones of that note lie compared with the things that have changed with the arching. Whereas the sort of passages we've been listening to with Glazunov or Tchaikovsky or what have you, just a couple of bars of real music gives you something that's much more anchored in musical experience. I mean, Jesus, I could easily supply a bridge force recording of a bit of a snatch of music, if you'd like to try that. I think you'll find it gives you it's just as easy to do if you've got convolution working already. It's just a matter of a different input file, and then you might find that quite revealing.
Yes, please do so. And I can send you the impulse response if you want it. Okay, but please do so, and we can test the experimental measurements.
Yeah. Send me an email when we're over, and we'll have an exchange of things. But I happen to have those conveniently to hand because we were playing with them last week when the bridge guys were here doing bridge adjustment testing.
Okay, so Doug Martin had his hand up. Doug, do you still have something to say or ask?
Well, everyone, Tori, Jesus, and the others all sort of were saying what I was feeling. So that's why I put it down. But yeah, you know, the difference between the tap and an actual note is well, you can't predict it without doing the convolution for every note, and you get as Joe said, it's a change of color and vowel quality that you know, initially it's unpredictable without further data. So that's my experience with various violins, that it depends on what note you're playing, what the quality is. That's
I don't know. I don't know. Understand if there is a question? No.
well, maybe does the definition that you have a comb effect of a frequency filter, so it's how the overtones intersect that. I think that was already said.
I think Doug's basically agreeing with Jim.
Yeah,
Okay.
Jim, that's what I'm saying. Yeah, Jim.
Okay.
Correct.
I need to say that, as Jim knows, and maybe fun, the notes that you hear are simulated. So we need to decide where is the maximum frequency, the highest frequency in a both note. So I don't know if this simulation is delivering the most interesting frequencies to analyze all these topics about how it's happening with the frequencies in what parts, because simulating notes from both for the both string is very complex too. So if we are hearing the tap tone, this is a very realistic sound. This is a very realistic sound, because simulating the impulse is quite simple, but simulating a note is very hard. So in the experiment proposed by Jim now, we can hear all these ideas mentioned by Douglas to hear what is happening now with a realistic response. So maybe in a future project, we can present something like that. So thank you, Douglas. Okay.
Well, one of the exciting things about this is simply getting to the point where we can have FEA models and then listen to them. So, I mean, we're a long way from, I mean, this is early work, but I really think it's the future of violin research in a lot of ways. So I hope you go ahead with this vigorously.
Yes, we're trying to keep only simulations, because in this way we can deliver to you the models, and do you need anything more? You can simulate your notes, your sounds, your changes in design without any other data, especially measurements. Measurements are hard to do in any part that is not laboratory. So we try to keep the part of only simulations. But thank you, Joseph.
And let me just add too that we now have convolution in the OBI app, so anyone can take an impulse response and convolve it with a musical example played by a real violinist on an electric violin, kind of a force signal that Jim was mentioning. So I think now the means of doing it is getting widely distributed, and anyway, bravo.
Jim?
I need the newest version then of the OBI app. Okay.
Yes.
I need the newest version. Okay. Yes. No.
Yeah. I wondered if it would be useful for people to hear what I was talking about, or just with a convolution with something more like real playing. If Fan would allow
yes.
me to
Yep.
share screen, I should be able to play something with a little bit of messing around.
Let me stop.
Okay.
Okay. I just talk amongst yourself. Well, I'll share my screen. No, needed to do the audio thing.
Well, while Jim's doing that, sort of as a intro to what he's saying, because in my experience, like if you take a real violin and you carefully listen to each particular note, like in a chromatic scale, each of the notes actually can sound quite a bit different to its neighbors. Okay, but somehow if you play a passage of music, your brain somehow is able to make sense of all of that and integrate it into some sense of the sound of the instrument. So I think that's just my example of the limitations of listening to just a single note in isolation.
Yes.
I'll be with you in a moment. Let's just randomly put. Are you seeing my screen?
Yes,
Yeah.
you see a waveform,
Yeah.
complicated.
I won't do a stereo one. You should, with a bit of luck, hear something. You hear that?
Yes.
Yeah. So that was one of the things that we generated during during the bridge gathering that some of us had last week. So that was a complicated mixture of a theoretical model of the bridge, a measurement of the admittance on a violin, and the measurement of the sound radiation from forces at the bridge feet. So we're doing the same kind of thing that Jesus was talking about, and we were looking at bridge adjustment. So that was one of a set of sound files with the same playing input, the same measured violin response, but different adjustments of the bridge rocking frequency or what have you. So I think we're pushing in just the same direction as Jesus, but did people, let me, you've heard enough from me sharing that. I think you learn more from that kind of brief musical snatch. For a start, it sounds more like a violin for a start. I presume, Jesus, the sound you were playing was using the admittance, was it, as your response function? That's another part of the story. The sound radiation is not, of course, the same as the admittance, and you capture some differences quite nicely.
Wasn't he using the impulse response from the tap, which wouldn't?
But it's the impulse response from the tap of his FE model, which I bet didn't have sound radiation.
Oh, I see. Yes,
it was the impulse response you'd hear with a velocity sensor on the bridge rather than your ear as such. Is that
absolutely
right? It was admittance.
No. Well. We decided that use the loudspeaker as the body of the violin, because in few words, we take the response in only one point of the sound box.
Okay.
Near to the island for one speaker, and the other speaker was left for the sound holes, for the A0 resonance.
Okay.
So we have 2 points of a violin in a stereo system, like only this point. Well, this is the main idea, because the bridge is not radiating sound.
Yeah. No, that makes sense. It's a good idea. We've gone one step further, but that needs more. We're using measured sound radiation. So
Yes.
we're using the model to predict the forces at the 2 feet of the bridge, and then using a measurement for the sound radiated to a given microphone position from those 2 feet, which is not it. What you're doing is a sensible step in the same direction, and it still has the same virtue. I think absolutely, as Joseph said, the ability to listen to anything coming out of the computer is a very powerful tool. So definitely carry on the direction you're going. But if you'd like that violin input file, that's one of 3 or 4 that I have. I can easily send you that.
Okay, so this is also a little preview of some of the things that Jim will be covering in some future as yet unscheduled presentation about his recent research into bridges that he's been doing with Joseph and others. So that's a little.
Yeah, absolutely. We can schedule that whenever you want. I've got enough to talk about, although aspects of the study are going to rumble on for some time, I think.
Are there any other questions or comments about this particular in terms of topic, in terms of the
Look, I have
sound?
one more thing to say. Please, just a minute. I don't want to cry, but this paper was rejected in several journals. But now it's accepted in the Revista Mexicana de Física, but they don't have a repository for the files. If you want the model, you need to ask to me. No, it's not like other models that you can download from the system of the journal. This is very sad news for me, because the model is not available easily. But you only need to ask me to use it, and all the paper say there's instructions to be used, to be employed. Okay, well, that's it.
Joseph?
Going back to your analysis of Caldersmith data, I mean, the difficulty of getting from tap tones to body is been a long-term one, and of course, Martin Schleske, who I see is here, did a early paper that was fairly convincing that way. Now, I wonder though, if one took, instead of the tap tones and mass, one of these impedance calculations such as Evans, I mean, the stiffness of the plates must be related to the B1 modes. Has anyone tried correlating the sort of Evan numbers with average B1 frequencies?
I think numbers. I think that I don't understand what is you saying. How is the?
Well, I'm not the person to explain it. Evan is here, but it's a way of assessing sort of the average. Well, Jim, the average stiffness to mass ratios. No, it's the frequency times mass averaged out over the modes.
Don't ask me. Evan can answer. He's here.
Yeah,
Evan.
it's basically a space average, real part of the mobility. So it's the characterization of a large plate, and you could derive that from the fundamental modes of the free plates. I'm using a lot of Jim's arithmetic in that process, but it's a straightforward type of calculation.
And Evan, would you expect that to correlate with the body modes in some way?
Well, what it is if you just have the frequencies and you just have the masses, you've got, two things going in opposite directions. This just kind of brings those two things together. So
you don't know whether it would correlate with the.
It collapses some of the data a little bit better. It's kind of also looking like the Harris number is another attempt at doing that. Harris's number is more intuitive and mine's more mathematical, but they're trying to do about the same type of thing. It's kind of characterize the full dynamics. So one of the problems about chasing just frequencies is it doesn't tell you anything about the dry point impedances or mobilities. And so you kind of want to take both of those.
So the Harris number is just for one mode. Yours is some sort of an average over a bunch of modes, right?
So both the data going into both calculations are the X and ring mode frequencies and the mass of the plates.
Okay, so Jim, would you think there'd be a correlation?
Look at the data. I mean,
Yeah.
it's got a better chance of having a correlation than any of those individual parameters taken. It's a logical combination of them, and it's a simple thing. So Jesus
Okay.
needs the numbers, and it will be easy to put that into your program and just take the same Caldersmith data and plot it, see what it shows.
That would be interesting because,
Yeah.
I mean, I can't imagine, you know, if the Evan number went up and the B1 modes went in the opposite direction. I mean, we are kind of reflecting the same thing, but how precisely, I don't know.
Yeah, if they all went in opposite directions, that'd be surprising. That it'll still be a cloud of points in one of his plots. The question is whether it shows a little bit more of a systematic trend through the cloud.
Yeah.
Okay. Oh, well, enough said.
Yeah,
Okay.
and we kind of looked at it using a lot of the Oberlin makers data. That was kind of the basis of, you know, checking it out. And that's my 2013 paper at well, help me, in Sweden, the Sweden conference.
Well, I think quite a variety of makers are now tracking. Did you call it the Z? Is that your termination?
This is a question for me.
No, for Evan.
Oh, okay, sorry. Thank you, for your help.
Do you call your calculation the Z number? I just hear it referred to as that. I wasn't sure whether that was from you or George.
Yeah,
or...
it's a space average impedance number. It's the drive point impedance of an equivalent large plate. It's a SEA type technique. There's nothing novel about it. I'm just taking engineering out of another field and applying it to the violin.
Well, it just seems like a lot of makers are now, or the kind of makers who do measurements are, I mean, they're taking the tap tones, et cetera, and they're calculating in various ways, and they're coming up with this and that and the Z number. And I'm not sure what they want to do with it or what one can do with it. I think George talks about it getting you in a range somehow, but anyway, this is just random thoughts about that. So if there was some sort of correlation with something else we could measure, it would be an added impulse to calculate it more. But I'll stop.
Yeah, Joseph, just to clarify, you know, George Stepani has talked about this, is that he does look at the Z number when he's graduating plates, not to necessarily hit, you know, a target number, but as a guide as to, you know, how far along he is in graduating his plates.
Mm-hmm.
I hope I characterized him.
That sounds right.
That's basically what George is doing. So it's he uses it as a guide to thinning, and there are places he doesn't want to go.
Yeah.
Evan, you could send the Stockholm paper to Jesus, couldn't you? That'd be the
Yes.
way.
I've got his email here at home, and I just requested all his papers, so I guess I'll have to return the favor.
Okay, so I have a question about a comment, Jesus, you made, which is that you said the bridge hill appears in the bridge mobility plots for both simulations and your measurements, even without the F-hole. So can you or other experts comment on that?
Okay, firstly, making the violin for this test was a challenge because we need to put the sound post without F-hole.
Yes. So how did you do that?
I don't know. Patricia is my student, and it was her task, and now he is answering all these questions about how she does that. Well, about finding the bridge hill without F-holes was a problem for me, because for several years I was making experiments with with the higher parts of the holes, and mainly because all my life we think that the beach, the holes, the points, the island was the most important part. But it was not true. It was a problem when the paper was in the review. It was a problem because it was questioning. It was making a question in a topic studied for several years. So the only thing that I can say now is it shall appear, and we need to do more experiments on violins. In fact, this is the conclusion of the paper. So it's a very dangerous topic, in my opinion. Okay.
Well, oh, sorry, Jim, go ahead.
Shall I just comment briefly on that? I wasn't surprised to see it there. The frequency had changed a lot. Without the F holes, your hill frequency was higher. I mean, ultimately, if the violin body was rigid, then you'd still see a bridge hill at the clamped feet resonance of the bridge at the original F rock frequency. As has been said lots of times, the flexibility of the bridge is in series with the flexibility of the violin body. So you still get a hill if you eliminate either one of those two things. So Janssen's bridge with no cutouts still had a hill because of the island. Your violin with no island still had a hill, partly because of the bridge presumably had cutouts and can rock. And, you know, there's still some twisting flexibility in the top of your violin. Without the holes, it'll just be, it'll be stiffer, and that raises the frequency, which is what you saw. So I think it's not surprising that the feature is still there. It'll always be there to some extent. What you're doing is pushing the frequency around, which makes a significant difference to the sound. And in terms of adjustments, you've got these two things in series. So whichever of them is weaker will always dominate. And so you made it so that the bridge was weaker than the violin, and that should have dominated. The Janssen experiment made the violin weaker than the bridge, and so that one dominated. But the fact that it's there was no surprise, I think.
But the reality for me, because I'm a noob, I think, I was expecting a flat response like a guitar. But now I understand that this is not possible, because for all the things that you are saying now. But we need to see with our eyes in our lab, and we think that it was enough to share in a paper. Okay.
Joseph?
So if I remember the graphs, the bridge hill, or the peak that I noticed, was maybe at 1.8 kilohertz, something like that, which was very low for an admittance peak. Or maybe I'm okay. So the red dotted is with the F holes.
I mean, solid line without F holes.
Yes.
Short dash, F holes, strike parts. Yes. The red line, strike parts only. Yes.
Okay.
Line.
And then the blue line is everything?
Yes.
Okay. So I see a big hump just below 2 kilohertz. Is that what you're referring to? Because it's not what. And Jim, is that what you're referring to? There's actually a bunch of things going on when we say bridge hill, and I think there's some confusions easily arise. Jim, what were you referring to?
Yeah, I was looking at that, not really remembering the frequency, but by the time you get to the blue one, it's gone down to 1500 or 1400, 1500. Yeah, so it's going down from 1800 to 1500 as the F-holes are cut, something like that. from
Okay.
this plot.
So we're just dealing with a rather flexible violin top. I mean, I would usually expect to see
Probably.
that around,
Maybe a rather
2.5,
flexible
2.8.
bridge as well. I guess that the bridge in this model may be fairly flexible as well. If you look at the highest frequencies, up in that between the 3000 and 4.2 kilohertz, the four plots are in the natural order, and 10 dB's variation. That's the traditional place. That's the roll off above the bridge hill, and that's having a big effect. That's always the thing you hear is that high frequency filtering. I mean, it's arguable the black curve has a hump and then another hump at 3 point something kilohertz. Not clear what that is in this model.
Well, what's odd to me is the peaks aren't exactly the place one would expect for radiation. About 1.9, and then another lobe at 2.1, then a dip at about 2.3, and then another one about 2.4 or 5. I'm sure it's coincidence, but that's why I was a little confused.
Okay, so I want to follow up because apparently guitars or flat plates that by themselves don't have this prominent bridge hill feature. So what is it structurally that's fundamentally different about guitars versus violins?
Flat bridge rather than a high bridge. There's no equivalent of that bridge rocking motion. If you strung a guitar body through a violin bridge or a cello bridge, suitably fitted feet, you'd get a hill.
Okay.
I don't know.
I'm sure that's the answer. That's what I said in the original paper. Anyway.
I don't know.
Yeah.
Any other questions from the audience? Wow.
Well, if no one's, if I'm not interrupting anyone, back to convolution, it occurred to me that, and this is very tangential to what we were talking about earlier, but it's tempting to put excerpts with a dramatic attack, such as in Cambridge you're using the Sibelius. But I wonder, is that deceptive because the attack isn't going to vary with the impulse response? I mean, that's a product of the bowed string. Shouldn't we be listening to rather sostenuto things in order to get a more realistic sense of what convolution is showing us?
No, that's my answer to that. That's
okay. And why?
What you want, well, if you want to use convolution to give you an overall impression of the whole frequency response of the instrument, then you want an input with lots of broadband stuff, and a scratchy attack is good for having wide spread of frequency content. If you just play a gentle note fading away again, then it will really only contain the overtones of that particular note. I think it's easier to tell instruments apart by playing martelets.
Okay, I buy that. Good.
So Joseph, can I add to that? Because in my experience, steady state static notes played on violins, there are far fewer differences I can perceive between instruments when I just play a steady state note. It's when the note starts varying in its parameters, and two of the most obvious ones, okay, are we just talked about the attacks of the notes, okay, which gives you a huge amount of information, and also with modern romantic violin playing, vibrato.
Oh, I agree with that, but my concern had to do with the players. You're approaching it from a player, and you would be the first to say that the you know, the playability, which is nothing to do with the, is not captured in the convolution, is what's that makes an effect on an attack. Anyway, I don't need to push that any further, but I agree with what you're saying, Fan.
Maybe we can hear, we can read the questions of the chat.
Oh, okay. Yeah, let's go to the chat. So, well, Jesus, you want to pick up the questions?
Well, it's not fair, but I am seeing the last question.
Okay.
Say Catherine is saying, so a 0F hole violin will be expected to be even less powerful despite not having much of a change in that spectrum. Really, the answer is I don't know.
Well, if you're talking about radiated sound or you're talking about admittance, I mean, they're very different, or motion at some particular body point.
Sound radiation is another history. Our model is only limited to vibrations. So when we are speaking of waves through the air, we are speaking about another system, including the wave number, for example, the wavelength of the wave, cancellations, and so it will be hard, at least for me, trying to predict sound radiation only, only having data in my mind of the vibrations. We need to do more calculations for answer this question. Okay. We can see another question. I am wondering how things will change if you had a single hole instead of the usual two. Scattering again. Well, we can try this in the model. Extracting a hole is pretty easy. You only need to say in the model what do you want, what do you don't want, and see what happened. This is the spirit of the project. I don't know, Fan. I read more message. I don't know. How do you think?
Well, so the other comment that so this is where we get into sort of a bit of a trouble, because what do we mean, for example, by complex sound? So we have Leo says, I agree with Tom that higher arch had thinner, less complex sound, and lower arch had darker, fatter, more complex sound. You know, but then I think the only thing we're in agreement about is that they sound different. But what do we mean by "quote unquote" complex sound? You know, and I think there's probably a general consensus amongst makers actually that in general higher arch instruments probably they would say have more complex sounds than lower arch instruments. Although the makers can correct me if I'm wrong. Jim, got your hand up.
Oh, yes. Jim Woodhouse said, and I agree, that the primary way that a guitar top vibrates, meaning a flat top guitar with a glued-on bridge, is quite different than a violin with a taller bridge. So that the the primary way it gets excited is rocking side to side, whereas I think with the flat top guitar with the glued-on bridge, it's rocking in the direction of parallel to the string. But what about an archtop guitar or a mandolin with a bridge that's not as tall and is much wider compared to a violin as a ratio? what's the primary way that they work? Is it more side to side or parallel to the string?
Let me jump in here. There's very little data that's been collected on that. But in the Selmer guitars, which are flat tops with carved bridges, and they have no adjustment screws, there is a sensitivity to the bridge design. And the frequencies of those look like Bridge Hillish type frequencies as a beam. Mandolin makers also refit their tailpiece bars, which is on jacking screws or metal screws. And changing that top beam is something that is used to fine tune the instrument. So those are two instruments that have higher bridges with feet separated. And if you want to have even more fun, go look at Jim Woodhouse's banjo page with the 3-footed bridge. All those bridges have some sort of dynamics with them, as opposed to the big slab on a flat top guitar or classical guitar.
Yeah, I was going to mention the banjo stuff. Yes, you can find some stuff on your phone, including some.
I did
files.
already look at your banjo stuff.
Yeah.
Being a out of the closet now banjo enthusiast myself.
Well, I want to comment something about the history that I understand about the measurement of the bridge mobility. I remember the papers and the work of Hanson over the years. In my opinion, he was trying to find a structural response similar to the sound radiation measured on the space, because measuring, in my opinion, measuring vibrations is easier than measuring sound radiation, because the space is involved. So I think, or I remember, maybe it's wrong, I don't know, that he was trying to find a measurement to substitute or to facilitate obtaining a response saying something about the sound radiation. So if we have bridge, a thaler bridge in a guitar, for example, and we are obtaining the bridge hill in the response, I don't know if this means bridge hill in the sound radiation. I don't know if my idea was clear. But the important thing in studying the bridge hill is the bridge hill is saying a lot of the predictions about the sound radiation. So trying to find bridge hill on guitars will be another very different topic, I think. And I want to comment that.
Okay, so I have a question back to the guitars, okay, about the direction of the string excitation force, which is that for guitars is the predominant excitation mode into the body of the instrument vertical or horizontal? Because for a bowed instrument, the bowing action forces the vibration to be mostly in one plane, but for when you pluck a string, it quickly starts to precess, and you've got vibrations in all, precessing in both planes. So, but for a guitar, bridge, which is the dominant excitation to radiate, the vertical or the horizontal direction?
Vertical is louder.
Vertical.
Yeah. And in classical guitar playing, players use two different plucking styles depending whether they want to emphasize the vertical or de-emphasize it, called tirando and apoyando, but the other way around. So the rest stroke, where you pluck kind of 45 degrees downwards and your finger comes to rest on the next string, puts a lot of vertical stuff in. If you pluck straight across, you get something with less low frequency and more quieter. So, guitarists use it for manipulating their counterpoint lines. If you pluck a string, if you really want to hear the effect, you should pluck your strings using the wire break pluck. So if you find some really thin wire, unwind an old pickup, you can put a loop around the string and pull it till it breaks and listen to the pluck. And if you do it that way, you can control the orientation really precisely. And if you then pluck right in the plane of the strings, it's very quiet. You pluck vertical and you struggle not to get a buzz against the frets. But apart from that, it's louder and more bassy.
And in an archtop guitar, the technique I was taught was, think about scooping ice cream. You're pushing down into the top and scooping out to give a big vertical kick, especially in the middle two strings of the guitar, which is the traditional rhythm guitar of the big band era. Also, with a old-fashioned fluorescent light bulb, you can strike an E string in any direction you want to and watch it process, and it very quickly locks into the vertical vibration mode as the dominant mode.
Does it gravitate to where there's the most admittance? Is that what happens?
Do you really want to know the answers to this? I think if you let things go long enough, then actually it will do the opposite to what Evan said, because there's the energy is taken out of the string more rapidly in the vertical polarization, so that will decay more rapidly. It's Gaby's famous paper on double decays. You get a double decay in a single string because of the horizontal and vertical polarizations. The vertical one is louder but decays faster. The horizontal one is quieter but rings on for longer, if the strings allow it. Metal strings, with nylon strings, everything dies away anyway.
So it's not the case that the actual mode is. So what's the definition of precess? I haven't heard that word.
It's doing a loop. So you strike in one direction, and all of a sudden you see the motion moving.
If you start a string vibrating in one perfect plane, if the terminations and the string was perfectly symmetrical and all that stuff, it would maintain that polarization. In real life, that's not true. So it'll some of the energy gradually gets converted into a different polarization, and often it'll precess. But with a plucked instrument, most of the characteristics of the sound is an initial pluck. So yes, so even if the string precesses, eventually the predominant direction of the pluck at the beginning does play the biggest role, as Jim pointed out, in the sound.
So with a violin, I just thinking about, Colin's interest in ringiness. The horizontal would be absorbed most quickly at most frequencies. So would the string be left vibrating predominantly vertically?
Okay, so here's
prominently on a line to the sound post. So it depends which string you pluck. But at low frequencies, the stiffest direction is towards the treble foot, where the sound post is, probably. So I would guess that it's the perpendicular to that.
So a couple of things, Joseph, on that I've observed. First of all, once you let go, there are certain types of bowing gestures where the bow leaves the string, and then the string will start to precess. Okay. That's towards the ends of the note. The other thing that I've observed is that different types of, there is a small vertical component to a bowed string, and that actually varies with the type of string construction. Typically, I found, but the last measurement I made was 20 years ago, that it seemed that the synthetic core strings had a larger vertical component.
How is that possible?
Well, there's because you've got a compliant system with the bow hairs and the bow, so the bow hair isn't rigid in the vertical space, so that's adds a additional complication to the bowed string that I'm aware of, but I haven't thought about mathematically how you would model this, but perhaps
So
Jim
you're
has.
you're pressing a soft string down so there's a greater angle at the bridge so you'd get more vertical?
Well, I'm assuming, but maybe Jim has some ideas and explain this better. Jim?
I think if you wanted to take this any further, you should review your 20-year-old measurements. You
No,
have to
I've
be
seen it.
really careful about what you mean by horizontal. On a violin, really careful
No,
about
okay, so
what you're
this is
talking about, yeah.
observed on you know, on a string test bed. I had X
On a-
and Y sensors, and I can see the
Ah,
the
That'll be-
vertical
that-
sensor. There's the amplitude of the signal on the vertical sensor. There is a
Yeah.
definite amplitude.
Yeah, there are several possible reasons for that, that it's probably rather remote from the subject of this talk, but the natural, on a test rig, the string presumably has rather rigid terminations in both polarizations. That means that the frequencies of the string are really very similar in the two polarizations. Whereas ordinarily they get split apart because the one that couples to the body will have its frequency shifted a little. Now, one view of the processing rate is that it's beating between those two different frequencies of the string. But if the frequencies are the same, then you're exciting by bowing in one polarization. There's always stuff going on. Your bow is not exactly horizontal. There's some kind of coupling. If the resonances of the other polarization are more or less exactly the same frequency, then they will get excited even though you don't put much input into it because they're resonating at the same frequencies. The synthetic chord strings, I guess, have slightly higher damping, therefore slightly higher bandwidth, therefore slightly more tolerance to the splitting of those two frequencies. So the modal overlap will occur more readily, maybe in that case. But that's all just hand waving and guesswork. I'd want to do the measurement, see the data, and do it carefully.
Yeah. No, this is a long time ago. But my impression was that the frequency of the vertical mode is the same frequency. You know, it's the same basic frequency as the horizontal. You know,
but it matters. It matters whether it's the same to within the bandwidth of those string resonances, which are pretty narrow. So it needs some more.
The vertical component was very large, you know.
Yeah, well,
it's it's on the order of 5 to 10%, 5%, you know, of the.
Yeah, but that's because it's resonating at the same frequencies. So in any kind of input from little bits of asymmetry in the termination details and what have you will evoke a resonant response. So you get more response than you were expecting because it resonates. That's plausible enough. Whether it matters for anything on a real instrument is another matter altogether.
I'm curious, Jesus, how at the violin making school you integrate measuring with violin making, or are they two distinct things? Do the students measure properties of the wood, the process, the finished result?
Previously to your question, I want to say that I think that the answer that Fanny is looking for is not available. I think that Fanny is trying to find a standard way to measure any guitar. We don't have this measurement. Well, at least in my hands, I don't know if this exists like it exists in the violin. In violin, we have a standard measurement to measure every instrument. And linking this with your question, Fan, or Joseph, today, just today, one of my students of the course of my classroom makes me a question. What is the the influence of the varnish in the instrument. So to answer her question, we are making a plan about the way to prove what is happening. Having the violins without varnish, the kind of measurement to do, the type of varnish, things like that. And after this process, we see that all the steps are available in our school. So we left the topics of the class, and from a few weeks ago, we only making this project. So they are creating their violins without varnish. They learned to measure the bridge mobility and the steps are in the next way. I am asking them measure their violins, several responses, but mixing them. I mean, student number 1, violin 1, then student 2, violin 2, student 3, and then another round, trying to find that they are learning to obtain the same response of the same instrument. They are measuring day by day, and when they obtain the similar bridge mobilities for the same instrument, now we are to proceed to varnish the instrument and repeating the process. If this gives us very important results or not, is not important. We're trying to teach to the students the question that you are saying. This is the way. This is the way to impart the class in Milan. Okay, Joseph.
Very good.
Yeah, that's great. So you're actually not just teaching theory, but you're actually doing actual measurements and experiments to teach
That's
them,
correct.
you know, a sort of in effect, a scientific method of analyzing problems.
Yeah, some of them looked pretty happy measuring in the lab. It's weird for me, but they are very happy for this.
Mm-hmm.
I wonder, have you been invited by other violin making schools to talk about this? It sounds like, is there communication between the schools as institutions on how they teach these things, I wonder? In my subtext is I would hope there would be, but I can imagine that there isn't.
Well, I can say that I don't know how to say that. Is more directly connected with another schools of engineering that with violin making schools. For example, let me share my screen. Well, this is the responses. This paper is about guitars, but I eliminated from this conference because it's the DSA. But we are showing the mobilities measured in the guitar. This paper of vibrations of a violin while the F holes were sequentially cut. It was measured in an engineering school, and the student of the PhD taking the interferograms is very interested to enter in a postdoctoral studies in our school. trying to link in violin making schools of other parts is not easy for us, but it's available to everyone if you want to try. Okay. Oh, no question.
Any other questions or comments on this? Well, let's give Jesus a great round of applause for the presentation and all the questions and issues that he has raised. So best of luck in your continued research to uncover more answers.